So we have a pretty good understanding of linear motion. Now let's see if we can extend this into understanding angular motion. So in a line, when we change a position, we typically denote that by change in x. In angular motion, the equivalent to change in position is going to be change in theta. Okay? So we can do this with all the variables that we typically study in linear motion, something like a velocity. Velocity we can define as a change in position divided by a change in time. I can do this in angular quantities. The angular velocity, which we use the Greek letter omega, is equal to the equivalent to the change in x for angular quantities, which would be change in theta, all divided by a change in time. So these are kind of drawing analogies between the linear quantities and their angular quantities. They're not exactly the same, but it's the same concept, the same kind of theory kind of applies. So in a line, we also have acceleration is typically of interest for motion in lines. That's the change in velocity over a change in time. And we can kind of draw an analogy to figure out how this works in angles. The acceleration for angular acceleration uses this kind of curly A, which we call alpha, and that is equal to change in omega over change in time, the angular velocity over the change in time. So we just learned a lot of physics for moving in angles just by drawing analogies for what we know how things move in lines, in linear motion. We can continue to extend our understanding of angular motion to understand circular motion by drawing kind of relationships between linear quantities and angular quantities. So for circular motion, let's say we're going to move in a circle. So here's my circle. We can describe how big that circle is by a quantity known as the radius. So that's from the center of the circle out to an edge. We can define a velocity that a point has on this circle. So maybe this point is moving around in the circle. Its velocity is going to move off tangent to that circle with a velocity of v. Now the whole circle could be rotating, or we can describe how fast this thing is going around the circle, not at this particular point, but the average velocity that this thing experiences as it's going around in this circular path. That is what would be your angular velocity. So what we need to do is relate the linear motion at the edge of circle, so this v, to what this omega actually is. So these aren't the exact same thing. The velocity when you're tangent to this circle, so that point just kind of moving off at this velocity in a tangent line, that linear velocity, vt, v tangent, is equal to the radius of your circle times omega, the angular velocity that you experience. Okay, and we can do something similar to figure out what the acceleration will be. So the acceleration of the tangent of this circle is going to be equal to the velocity tangent to the circle point, all divided by the change in time. So again, it's still just velocity over change in time, and I can take this vt and I can substitute it in to find out that the tangent acceleration is equal to r times omega divided by change in time. So all I've done there is a substitution. So the acceleration at the edge of a circle, acceleration at this tangent, is equal to the radius, r, times the angular velocity, all divided by the change in time. So we've kind of learned how things work in circles now. We know tangent velocity is r times omega. So linear velocity moving off in a line is the radius times your angular velocity. And that helps us to get what the angular acceleration is, what the linear acceleration is rather at the edge of a circle. Acceleration at the tangent point is r times omega divided by change in time. And we can keep extending this. We can keep extending this to understand how kinematics work in angular motion. So we can also understand kinematics and how things move in angles by drawing analogies between the linear equations for kinematics. We should recall that there are three of these, three different equations, and we're just going to write them in their angular versions. So the angular velocity, final, is equal to the angular velocity initially plus the angular acceleration times the change in time. This should look familiar. This is just the linear equation written with the angular terms. So this will apply just as well as the linear equation. So we also have change in theta is equal to omega initial times change in time plus 1/2 times alpha, the angular acceleration, times the change in time squared. And then finally we have omega final squared. This is equal to omega initial squared plus 2 times alpha times change in theta. We got to these equations just by remembering the 3 linear kinematic equations and writing them in their angular terms. And we can do this, we can continue this kind of concept by looking at forces in rotational motion as well. So if I'm going to continue studying how things work in circles, I need to think about forces and how forces relate to circles. And the concept of forces moving in rotation is something called rotational inertia. And as we've been doing, we've been drawing kind of analogies between linear quantities and angular quantities. The inertia's linear equivalent is basically going to be mass. So if I think about mass and mass moving around in a circle, I can't use just plain mass. I need to use what's called the inertia of an object to replace mass for when I'm moving in circles. And the inertia is equal to the sum of all the mass that makes up your object, and it's multiplied by r squared, which is where all the mass is actually located. I need to account for both the mass and how that mass is distributed. Okay? And I can think about this in terms of an ice skater. So let's draw an ice skater in 2 different situations. I have my ice skater with her arms out, and I have an ice skater with their arms in. Okay, so if I think about these 2 situations, the ice skater with the arms out and the ice skater with the arms in, I can think about them spinning around, think about them rotating. So that's what ice skaters do. They like to rotate. They spin around. With my arms out, I can look at my mass. I can look at my rotational inertia. My inertia with my arms out is going to be a very big number. Now the mass of the ice skater doesn't change between situation 1 and situation 2. But what does change is my moment of inertia with my arms in becomes a small number. And the reason for that is because with my arms out, my arms are very spread out. So since my arms are spread, with the arms spread, I have a big R. So R is very, very large when my arms are spread out. So my R in this moment of inertia equation becomes large, and my moment of inertia becomes big. Now when I bring my arms in, my R decreases a lot. I get a much smaller R. So because of that, my moment of inertia becomes small with my arms in. And there's an effect that this results in called conservation of angular momentum. So we can keep understanding how linear and rotational quantities are related by studying how this moment of inertia change results in a speed change for this ice skater. So what's going on for this ice skater? Well, we know the concept of momentum from studying how things move in lines. The concept of momentum is that you have this P, momentum is equal to an object's mass times its velocity. Well, we need an angular equivalent for this linear equation. The angular equivalent is L, which stands for angular momentum. equals the angular equivalent of mass, which we just discussed is I, times the angular velocity of omega. And we know momentum is conserved. We know momentum before, momentum initial, has to be equal to momentum after, momentum final. So correspondingly, we know that angular momentum initial has to be equal to angular momentum final. And now I can study this again in terms of my ice skater. So let's draw my wonderful ice skater again. I'm such a wonderful artist. We've got our ice skater, and the ice skater has their arms out initially, and in the final situation, we have the ice skater, and they've brought their arms in. I'm sure everybody has seen this, and we know that when the skater brings their arms in, they speed up. So their speed is much higher. Speed increases. And the reason for this is entirely due to this conservation of angular momentum. And now we can understand physically why this happens. So initially, L initial has to be equal to I initial times omega initial. Their moment of inertia times how fast they're actually going. And L final has to be equal to I final times omega final. So let's see if we can use what we know about moments of inertia and this angular momentum being conserved to figure out why the speed increases when the skater brings their arms in. So we can think about this in terms of if these are big or little numbers. So with my arms out, my moment of inertia is very big. So I have a big I. And with my arms out, the skater's skating very slowly. Their angular velocity is very small. So I have a big number multiplied by a small number. We're trying to figure out what happens to angular velocity. So we're trying to figure out what omega final becomes, how omega final is affected by all of this. So I can look at what I final is. In the final situation, I final, with my arms in, becomes a small number. Because my radius is very small, my mass isn't very spread out. So I have a small moment of inertia times whatever omega final is. Now I know that omega final, that L initial and L final are equal to each other. So I know that my left-hand side has to be equal to my right-hand side. So what I have going on here is a big number multiplied by a small number. And that has to be equal to a small number multiplied by whatever omega final is. So I can divide both sides by this small number. So I'm doing algebra on letters, basically algebra on words. So my small on the right side cancels out with the small on the left side because I divide it out. So then I can see omega final is then going to give me a big value. So my speed increases entirely because angular momentum is conserved. And it depends on these moments of inertia, this mass, and how that mass is spread out. Okay? The final thing we need to talk about for angular motion in studying and understanding how things move at angles is just a quick corollary between linear and angular energy. So if I'm moving in a line, I have some kinetic energy. That kinetic energy is equal to 1/2 of my mass times my velocity squared. Now, if I want to figure out what this is for rotational motion, I need to use my analogs. So rotational kinetic energy, very easy to find as long as we remember these equations from previous kind of studies. Kinetic energy, if I'm rotating, we'll call it K rotational, is equal to 1/2 the rotational analog to mass. The rotational analog to mass is going to be I times the rotational analog of velocity. Rotational analog of velocity is angular velocity squared. So this gives you your rotational kinetic energy. Okay. The other kinds of energy that we know about, we also know about potential energy. Potential energy is equal to mass times gravity times height. You can see there's not really any angular values in there, anything that we need to replace angular-wise to get an angular potential energy. Um, and same thing is true with the potential energy due to a spring, which we saw was 1/2 kx squared. There's no real need to figure out an angular quantity for this. So the potential energies we don't have to really worry about for angular changes. We only have to worry about this kinetic energy to get rotational kinetic energy.